Swayam Prabha. Digital India. Educated India.
In this lecture, let us continue discussing the viscous compressible flow governing equations, and then we will also begin discussion on boundary layer equations for compressible flow. In the previous lecture, we had discussed about the energy equation, and you may be able to recall the assumptions that were involved while writing down this energy equation. So, we are recapitulating those assumptions once again over here, and based on that, once you write down this equation, you then introduce some additional non-dimensional terms over here involving the specific internal energy, the square of the velocity, the thermal conductivity and temperature, in addition to the ones which were already introduced when we non-dimensionalized the x momentum equation. Having done that, we saw that the energy equation came up in this form, and then if you divided all the terms on the right hand side by the term that you have as a coefficient on the left hand side, then it further becomes like this. So, there are these new coefficient terms forming on the right hand side, and one of the coefficient terms that is on the left hand side that you had earlier goes to 1. And now, if you analyze those right hand side coefficient terms one by one. So, one of them is this, that is expressed in the form of gamma and m infinity square. This coefficient is expressed in terms of gamma, Prandtl number and Reynolds number, where we already introduced the Prandtl number definition here, mu Cp by k. So, Prandtl number is proportional to the energy dissipation through friction and energy transport through thermal conduction. So, you may recall that we talked about viscous dissipation in the boundary layer, and this energy dissipation by friction has to do with that. The collection that you see over here is linked with gamma, and the last one here is linked with gamma, m infinity and Re infinity. If you put all those things together, now you see those new forms coming up over here in the form of coefficients, and all the terms within the bracket that you have on the right hand side, or these terms on the left hand side, are in terms of the non-dimensional quantities, therefore, those dashed quantities. Now, if you put all the governing equations together, this is how they should be looking like. In addition to the homework that I already gave you to find the non-dimensional forms of the y momentum equation and the continuity equation, please include this also as a homework to derive the non-dimensional energy equation. That would be interesting to do. Now, when it comes to solving the governing partial differential equations, you would need suitable boundary conditions that would need to be imposed. And here, of course, we are not yet getting into the discussion whether those 4 equations alone are self sufficient in terms of solving all the non-dimensional dependent variables that we would like to solve. We will take that discussion up a little later, but provided we have adequate number of equations which can be simultaneously solved, even then this issue has to be addressed, that suitable boundary conditions need to be imposed for the solution. Now, for solving viscous flow equations, we know that no slip velocity boundary condition has to be imposed at the wall. That means, the velocity components at the wall Here this being 2D, u and v both have to be equal to 0. Additionally, if it is a 3-dimensional situation, then w also has to go to 0. If there is mass transfer happening at the wall, now the question is why it should occur at all. This could be because there is some ablation or transpiration cooling which is being purposely done to maintain the surface at a safe temperature and not allow it to get heated up to unsafe temperatures. In that case, the wall boundary condition would be slightly modified compared to what we defined here. You would have u equal to 0 still, which is basically the streamwise velocity component coming to 0 at the wall, but the wall normal component will no longer be 0. It will take up a non-zero value based on whether it is an ablation or it is a cooling fluid that you are introducing. This is a wall boundary condition with mass transfer, where V n is the specified velocity normal to the surface. This subscript n stands for normal, wall normal. Thermal conduction is occurring at the wall, therefore, there is energy transport through the conductive heat transfer mode. We require an additional boundary condition at the wall involving either temperature or internal energy. So, you either have to specify in terms of T or in terms of E. If the wall is maintained at a constant temperature, then the constant wall temperature boundary condition shows up like this: T is equal to T wall. W stands for wall. This is called as the isothermal wall boundary condition. This T W is of course a specified wall temperature. In high speed flow problems, more so for hypersonic flow problems, the wall temperature is usually one of the unknowns. Now, that complicates the situation, because in the earlier slide we said that we are going to impose a certain value of the temperature at the wall, but then if it is very difficult to pose that wall boundary condition, because we do not have much clarity about what temperature will actually show up at the wall, then it becomes an unknown. Thus, using an isothermal wall boundary condition may not be practically possible or feasible. Instead, a more general condition is given by the Fourier's law of heat conduction in terms of the heat transfer rate. So, instead of talking about the temperature being imposed at a specific value, we may have more clarity on the heat transfer rate that we can allow at the wall, and based on the Fourier's law of heat conduction, then in that case we can specify the temperature gradient at the wall, which would accordingly fulfill that heat transfer rate equation based on the gradient and based on the thermal conductivity. So, Q W is the heat energy per second per unit area moving into or out of the wall. Into the wall if the wall is cooler than the flow, out of the wall if the wall is hotter than the flow. N is the coordinate normal to the wall, and therefore, del T del N is the normal temperature gradient existing in the gas immediately next to the wall. For the above boundary condition implementation, you need a separate heat conduction analysis describing the heat distribution within the surface material. So, you have to go below the surface and conduct a separate calculation for the surface material itself, and therefore, both the flow problem and the surface material problem, they have to be solved in a coupled manner. So, the problem does not seem to be so easy. A special case of the above equation, that means this equation, is the adiabatic wall condition, wherein by definition the heat transfer into or out of the wall is 0, which means Q W is 0, and when can that happen? When your temperature gradient goes to 0, and this is basically the condition of an adiabatic wall, a wall which does not allow any heat transfer, because the temperature gradient has gone to 0, there would never be a heat transfer irrespective of whatever thermal conductivity exists. The boundary condition of this kind can be achieved if you have a perfectly insulated wall. So, perfect insulation alone can create that. So, let us take note of that. Perfectly thermally insulated wall would give you this adiabatic condition. The boundary condition is not on the wall temperature, it is on the temperature gradient, 0 gradient condition at the wall. Now, the resulting wall temperature, which is not known a priori, would emerge as part of the solution, and that is what is defined as the adiabatic wall temperature. It is also called as the equilibrium temperature. As you can understand that when the free stream Mach number is large, there will be a lot of aerodynamic heating, and consequently, in order to reach this 0 temperature gradient condition at the wall, the flow gets more and more heated up, and therefore, more heat transfer occurs at the wall till you reach an equilibrium temperature, which we are calling as the adiabatic temperature, and in all probability a higher Mach number would correspond to a higher adiabatic wall temperature, because there is a lot of heat generation in the flow. It flows into the wall. If the wall is cooler than the flow, which is more often the situation, and therefore, till it reaches an equilibrium temperature, this heat flow continues, and where there is a lot of heat flow, there is correspondingly a larger wall temperature which is achieved. So, this is kind of intuitive, but you can understand that the adiabatic wall temperature definitely has a bearing with the Mach number of the flow. In most of the high speed viscous flow computations, one of the two extreme conditions are assumed. Either we use the constant wall temperature, that is the isothermal wall case, or an adiabatic wall. So, either this or this. To sum up, we have now seen that there are a couple of similarity parameters which govern the flows, and they are namely gamma, m infinity, Re infinity, Prandtl number, as well as the temperature ratio, because there will be some kind of a scaling between the wall temperature and the free stream temperature, which we will define as the free stream temperature ratio. We will see that this temperature ratio plays a very big role in compressible boundary layer calculations. Now, let us look at the boundary layer equations for not only hypersonic flows, but in general compressible flows. As you may be aware from your earlier courses of fluid mechanics or fluid dynamics or aerodynamics, that we often talk about an order of magnitude analysis when we discuss about the boundary layer equations. You may have looked at the Blasius solution, for example, for a flat plate when you have an incompressible boundary layer, and this order of magnitude analysis is very useful in reducing the compressible Navier-Stokes equations. So, when you learnt about the Prandtl's theory of the incompressible boundary layer, I think you should have come up with this analysis. And in the compressible Navier-Stokes equations also, this order of magnitude analysis plays a pivotal role, and the main intention is to reduce the governing equations to the simpler form, which we call as the boundary layer equations for compressible flow. And why we are interested to derive such an equation is because it can be solved with much less difficulty. The trends and patterns can be derived out of such a solution much more easily than solving the complete Navier-Stokes equations. Just to recall, if you were to sketch a typical boundary layer on a flat plate, here is your free stream velocity, here is a typical length scale, let us say the length of the flat plate, here is the formation of the boundary layer, a thin layer adjacent to the surface where the viscous effects are confined and the flow beyond it is basically invisible. To begin with, the continuity equation in its non-dimensional form, that is what we state over here, and then we will try doing an order of magnitude analysis of this equation and try to see what comes out of it. Here is a velocity profile, typically what we see within a boundary layer, with u equal to 0, typically v also equal to 0. The streamwise velocity reaching nearly u infinity velocity over a small length scale delta, where delta is much less than c. And going ahead with the order of magnitude analysis of this continuity equation, we need to take note of a few points, that the u dash, which is nothing but u by u infinity, it varies from 0 at the wall to a value of 1 at the edge of the boundary layer, and therefore, we can call it as having an order of magnitude equal to 1, which is represented with a nomenclature like this. If you look at density, for example, the rho dash term by definition is rho by rho infinity. There will be minor variation in density within the boundary layer, and therefore, the rho dash typically is of order 1. The x dash, which varies from 0 to 1 from the leading to the trailing edge of the flat plate. This is the chord length of the flat plate, or simply the length of the flat plate, and thereby x dash gets an order of 1. Now, coming to y, it varies from 0 to delta, that is the extent of y within the boundary layer, and remember that delta is much less than c. When it comes to y dash, defining y dash, it is of the order of delta by c, and since delta is much less than c, this ratio is also much less than 1. We will call it as order delta. So, this is a kind of a, it is an odd man out, as we say, because all the remaining terms that we have seen till before this all were of order 1, while here we have a term which is of order delta, delta being a very small number. If you wish, you can also call it epsilon. Substitute these above orders of magnitude that you have already obtained into the different terms of the continuity equation. So, here is your continuity equation and you go term by term, but instead of looking at it in the form of partial derivatives, try to look at it as product of orders of delta rho dash and u dash here and divided by order of x dash here. Similarly, the second term in the continuity equation. So, if you try to look at it that way, you have product of two orders here, that of rho dash and u dash, and order of x dash in the denominator, all being order 1 terms. Now, since the right hand side is equal to 0, we expect that out of the second term also the outcome will be an order 1 term only, so that they negate each other and finally, the result goes to 0. Now, the first term we know, that is rho dash. The second term we do not know, so we just put it as v dash order, and then the denominator we know, it is order delta, that is due to y dash here. It is apparent from the order of magnitude of the terms that the v dash has to be of order delta, so that finally, this collection of terms becomes order 1. That means, v dash is very, very small within the boundary layer, unlike u dash, which is of order 1. Let us look at the x momentum equation term by term now. We have indicated some 5 terms a, b, c, d, e, and then going one by one, the a term put together its order 1, because all the individual terms, whether in the numerator or in the denominator, all are of order 1. Going to the term b, Notice that this is order 1, while V dash is of order delta, U dash is order 1, but Y dash is of order delta, and this and V dash cancel in the sense that they give finally an order 1. C gives us an order 1 because the terms in the numerator and denominator both are of order 1. So, P dash, which is nothing but P by P infinity, the pressure typically within the boundary layer is going to change very insignificantly or practically not, and therefore, through the thickness of the boundary layer, the P dash is always of order 1. Going to the term D, you have a order delta term here. You have a order 1 term here where we are talking about the viscosity coefficient, which is of the same order as mu infinity. A little change here and there based on temperature variation and so on when you have a very intense viscous dissipation, but it is still of order 1. V dash, it is of course order delta, and consequently, since you have two terms of order delta in numerator and denominator, finally it does not affect and you have a order 1 term here. Going to the term E, you have order delta in the denominator here, order 1 here, again order 1 here, and so two order delta terms here in the denominator will finally create an order of 1 by delta square in the E term. Putting these findings together, we have a situation like this. Now, we still have not committed about the order of this term, but in the boundary layer analysis we consider that the Reynolds number, the free stream Reynolds number is pretty large, and therefore, since it comes in the denominator in this coefficient, we can imagine that it is order delta square. We take it as delta square to make sure that it is really large. If it was order delta, then it would have meant that it is moderately large. So, the terms involving RE infinity in terms of order of magnitude would then figure like this. So, you now have an order delta square sitting outside the square bracket in the form of a coefficient operating on these two terms. So, what will happen inevitably is the first term, which was of order 1, when multiplied with this would become very small. It would basically become of order delta square, and therefore, you can neglect it because it is a really small term. While when you multiply this with the second term, which is of order 1 by delta square, you end up getting an order 1. Therefore, that is retained, because all the remaining terms that you have are basically being retained, and all of them happen to be order 1. So, finally, the boundary layer form of the x momentum equation in non-dimensional form comes up like this, where you now know that one of the terms, one of the viscous terms has been dropped. When this equation is written in terms of dimensional variables, you see that it is showing up like this. Now that we learned the process, we can do the similar thing for y momentum equation. So, we begin with the non-dimensional form, perform the order of magnitude. Let us do it quickly. You will find that the first term has an order delta, and that is basically defined by the V dash having an order delta. The second term is also of order delta. It is defined by the V dash and Y dash both being delta terms. So, there are two terms involving V dash in the numerator, while one involving Y dash in the denominator, and consequently, the outcome is an order delta term. Then on the right hand side, we are not committing about the order of this, but rather moving on to the viscous terms. We impose the order delta square for 1 by RE infinity, and then moving into the terms within the bracket, you can see the first term will be of order delta because of the V dash, which is of order delta, while all others are of order 1. While in the second term, you have an order delta because that is basically coming only from one term of order delta. Therefore, finally what do you have when you put the things together? We make an assumption at this point that if this term gamma m infinity square, which is a coefficient acting on the pressure gradient, happens to be of order 1, which is true when the m infinity is not too high, then the pressure gradient term will be of order delta. Why is it? Because if you go back to this equation, you can clearly see all the remaining terms here, they are of order delta, right. So, this establishes the fact that this also is going to be of order delta if this condition is fulfilled. The dimensional form of the y momentum equation simplified based on this order of magnitude analysis would then be del p del y equal to 0, which is a familiar outcome. We saw this happening even in the incompressible boundary layer theory. However, if m infinity square is very large, and that can happen in the hypersonic range or hypervelocity range, then the 1 by gamma m infinity square will no longer be of order 1, but will be of order delta, in which case the pressure gradient term can become order 1. Therefore, for very large Mach numbers, the assumption that the pressure is constant in the normal direction along the thickness of the boundary layer is not valid, and there is a normal pressure gradient within the boundary layer for large m infinity. This is a significant difference in compressible boundary layer in the high Mach number limit. Coming to the conclusions of this lecture, in this lecture we discussed about the governing conservation equations of viscous compressible flow with an emphasis on similarity parameters. We started discussing the compressible boundary layer equations and we made some progress. Thank you.